Hey everyone, and welcome to This Explainer. Today, we're taking on a genuinely fascinating goal. We are going to totally demystify neural networks. We hear the term machine learning thrown around all the time. It's like this massive magic buzzword. But today, we're going to break it down into a really relatable, highly structured mathematical story. We are completely unpacking the black box to see exactly how a computer actually learns to perceive the world around it.
Okay, so let's set the stage by contrasting two totally different worlds. Think about your own brain for a second. Even if you're looking at a super messy, low-resolution number 3, your brain has absolutely no trouble recognizing it, right? But imagine sitting down at a computer to write a step-by-step program that takes a grid of 28 by 28 pixels and outputs a definitive number from 0 to 9. Suddenly, this comically trivial human act becomes a dauntingly difficult, almost impossible coding challenge. So how do we bridge that massive gap?
To really deconstruct this challenge, we have to start with the absolute simplest building block of our network, the neuron. Now, when you hear the word neuron here, just completely forget all the messy biology for a second. Instead, think of a neuron as just a simple container holding a single number, specifically a number between 0 and 1 that just represents the grayscale value of a pixel, 0 for completely black and 1 for perfectly white. We call this number the neuron's activation. Basically, think of it like a little light bulb. A high number just means the neuron is brightly lit up. Now, what's really fascinating is how we structure these simple neurons chronologically into distinct layers. We start with the input layer, that's our 28 by 28 grid, giving us 784 individual pixel neurons. Then we feed those right into what we call the hidden layers. In our model, we're looking at 2 layers of 16 neurons each. And finally, everything cascades down into the output layer, just 10 neurons, each representing a digit from 0 to 9. The entire magic of this system lies in how the activations in one layer trigger or cascade into the activations of the next. But why organize them in layers like this in the first place? Well, let's compare the network's structural layers to how we humans actually learn. We intuitively break down complex visual shapes into basic subcomponents. Think about it. A 9 is really just a loop up top and a straight line on the right. An 8 is just a top loop paired with a bottom loop. A 4 breaks down into 3 specific straight lines. Our brains effortlessly piece these subcomponents together to build a larger pattern. And honestly, we hope the network's hidden layers operate in a very similar way. The whole goal of this layered structure is a progression of abstraction. So the first hidden layer might act as a detector for tiny, specific pixel edges. Then the next layer combines those tiny edges into larger shapes like loops and long lines. Finally, that last layer combines those loops and lines to recognize the final digit. It's like this incredibly elegant, step-by-step assembly line of visual perception. So the million-dollar question is exactly how these layers connect to one another. They use what we call weights. You can basically picture weights as visual dials or knobs. They are essentially numbers that represent the strength of the connection between a neuron in one layer and a neuron in the next. By dialing these weights up or down, the network can tune into very specific pixel patterns, like an edge in a particular corner of an image. If the weights are dialed in correctly, the neuron only lights up when that specific pattern is actually there. But weights alone aren't quite enough to make it work. Alongside weights, we introduce a concept called bias. A bias is just an extra number added to our weighted sum. It establishes a strict threshold. It's essentially telling the network, hey, do not light up this neuron unless the incoming signal is really, really strong. It dials in exactly when a neuron should trigger its activation, which perfectly prevents the network from getting confused by weak or noisy signals in the image. Now just imagine the horrifying but kind of fun thought experiment of sitting down at your desk to manually tweak 13,000 individual knobs, weights, and biases in this simple vanilla network. You'd have to perfectly balance every single dial so that the layers accurately pick up on edges, then shapes, then digits. It perfectly illustrates the terrifying complexity hiding inside even the most basic neural network. But you know what? That complexity shouldn't scare us. Instead of seeing a neural network as some impenetrable, magical black box, treating this massive network as a mathematical function actually empowers us. Because when things go wrong, and believe me they will, knowing what those 13,000 weights and biases are actually doing gives us highly practical debugging tools. It allows us to peek under the hood, challenge our assumptions, and expose actual structural solutions, rather than just blindly guessing. So how on earth do we actually manage all those numbers in code without writing out 13,000 separate equations? Linear algebra. We pack the activations into neat column vectors, the weights into matrices, and the biases into added vectors. And by doing this, we can compute the massive web of connections using incredibly fast, highly optimized matrix multiplication. It literally turns a chaotic web of 13,000 connections into extremely tight, clean, and simple code. When you zoom all the way out, the entire network is really just an absurdly complicated mathematical function. It swallows 784 numbers representing an image, churns them through a massive matrix of weights and biases, and spits out 10 numbers representing its final guess. It's wonderfully reassuring, isn't it? The system has elegantly evolved from a loose biological analogy about brains into pure, highly structured math. Now, there is one mathematical hurdle we haven't covered yet. How do we ensure the numbers stay neatly between 0 and 1? Well, early on, engineers used something called the sigmoid function. Think of it as an old-school squishification tool. Because early designers were trying so hard to strictly mimic how biological neurons are either perfectly active or perfectly inactive, they used this mathematical curve to violently squish any weighted sum, no matter how massively large or small, right into that tight 0 to 1 range. But modern networks? They realized they didn't need to be so biologically strict. We've largely evolved to use a function called ReLU, or rectified linear unit. And it's actually shockingly simple. It just takes the maximum of 0 and the input. If the incoming number is negative, it just outputs 0. If it's positive, it acts as an identity function and just passes the number straight through. When we put these two head-to-head, it's pretty clear sigmoid is mathematically messy and notoriously difficult to train as networks get deeper. ReLU, however, is a brutal mathematical simplification. It turns out that completely ditching the strict biological analogy for the sheer computational efficiency of ReLU is exactly what made today's incredibly deep, wildly powerful neural networks possible. Sometimes abandoning biology for math is the absolute key to progress. And why does this progress matter outside the lab? Because this layered, efficient math unlocks immense business value. Once you have a machine that can scale its pattern recognition, it doesn't just stop at reading handwritten digits. It scales up to automate parsing raw human audio into syllables and words. It seamlessly translates those syllables into abstract thoughts. It automates massive, large-scale visual data processing. This is quite literally the engine behind the automated modern world. To wrap up this explainer, we are left staring at the ultimate question. We know it's a massive mathematical function. We know there are 13,000 unprogrammed dials, weights, and biases waiting to be tuned. But if no human programmer is sitting there manually twisting those knobs, how does the machine actually learn to set them on its own just by looking at raw data? That is the true magic of machine learning, and it's exactly what you should be wondering about next.